Hello all! In this video we are learning to draw Lewis dot structures for covalent compounds, or maybe we can think about this as a relearning. A few of our compounds will get a little bit more complicated than what we saw in pre-AP chemistry. But these Lewis dot structures are formulas, little drawings we can make to model what our compounds look like within something that's covalently bonded together, sharing those electrons between nonmetals. Nonmetals are always sharing electrons to get 8 valence electrons and be stable. So rather than that complete transfer of giving and taking, they're sharing it, which we have seen represented in those little lines between elements that represent 2 electrons being shared. We have several rules / hints to draw these Lewis structures. First thing is our hydrogen is always going to be a terminal atom. Hydrogen is an exception to this rule of having 8 valence electrons because it only needs 2 to be stable to get that full valence shell. So it will only be connected to one single atom. It can only form one other bond. When drawing a Lewis structure, one of the first steps is going to be to pick out the central atom. The central atom is normally the lowest electronegativity atom, with the exception of hydrogen again because it has to be on the outside. It has to be a terminal atom. We'll also need to draw Lewis structures for polyatomic ions. Polyatomic ions are a group of atoms that are covalently bonded together, and that whole group has lost or gained electrons, so it has a charge. We are going to take away or add electrons to the central atom. So positive ions have lost electrons. We're going to take those electrons away from our central atom. Negative ions have gained electrons, so we're going to add those on to the central atom. Once we have our Lewis structure, we're going to close it up in some square brackets and put the charge of that ion on the outside. Whenever we're drawing a Lewis structure, our elements are always going to start with one single bond to that central atom, but some elements are going to form double or triple bonds. The elements that generally will form double and triple bonds are our CNOPS elements: carbon, nitrogen, oxygen, phosphorus, and sulfur. And like we said, some of our molecules that we draw this unit are going to become a little bit more complicated than what we saw in pre-AP chemistry because they're going to have more than one central atom. Whenever we have more than one central atom, the formula is going to help us figure out what that Lewis structure should look like. So let's talk about a quick little example of that. So at the top here we have a little example of this more than one central atom case. Well, we know all of these hydrogens have to be terminal, so we can kind of break it down from there. Each carbon then, after it, has what is attached to that carbon. So this first carbon has 2 hydrogens attached to it. We have a second carbon, but the second carbon, so we got those guys, the second carbon only has 1 hydrogen attached to it. And then this third carbon has 2 oxygens and then a hydrogen as well. That hydrogen is actually coming off of our oxygen here, since it's going to need to be terminal. And then we can think about our rules of how many bonds these things should have, which we'll see here in just a second. So carbon typically likes 4 bonds, so this first carbon needs 2 more. It'll have a double bond there, giving it a full valence shell of 8. This carbon needs 1 more. Oxygen likes to have 2 bonds. So this oxygen gets 2 bonds, 1 to carbon, 1 to hydrogen. So something like that. But you can see that this formula, we have our CH2 part, we have our CH here, and then we have the COOH, helps us figure out that structure. So you'll see some more practice on all of that. The last helpful hint and thing to keep in mind to help double check that our Lewis structures are correct is that the total number of valence electrons in our Lewis structure must add up to the sum of the valence electrons for all of the elements in it. when also taking into consideration the addition and subtraction of any electrons for polyatomic ions. So basically, all of the valence electrons that are coming in for bonding, all the valence electrons that we start with, we have to end with. They're just sharing them. They're not going to be gaining or losing any more electrons than what they already have, with the exception of those polyatomic ions. The last helpful hint here is most covalent compounds, not all of them, but most of them, will be able to determine how many bonds each atom is going to have by looking at their Lewis structure. The paired electrons within a Lewis structure tend to not form bonds, while our single electrons will form a bond. So something like beryllium has 2 valence electrons, so it tends to form 2 bonds. Hydrogen's also on there. Hydrogen just has 1 valence electron that's single, so it forms the 1 bond. Boron has 3 valence electrons. When we do the 1 on each side as we should, 3 are single, so it tends to form 3 bonds. Carbon has 4 valence electrons, all single. They tend to form 4 bonds. When we get to nitrogen, when we put 1 on each side before we pair up, it ends up with 3 single electrons. It tends to form 3 bonds. Oxygen has 6 valence electrons, 2 are single. It tends to form 2 bonds. And lastly, fluorine has 7 valence electrons, 1 single, so it tends to only form 1 bond. These same general tips hold true for elements within the same group because they have the same number of valence electrons. Alrighty, so now we're going to look at some example of drawing these guys out. So when looking at these Lewis structures, generally the first thing we want to do is pick out our central atom. So which CH4, our central atom, is going to be carbon. Hydrogen we know has to be terminal, so we're going to spread all of our hydrogens out around it. We can go ahead and give each of these elements their valence electrons. Carbon has 4 valence electrons that it's bringing to the table. Each hydrogen has 1 valence electron that it is bringing to the table. Once we've added all those valence electrons, so carbon has 4, each hydrogen has 4 for a total of 8, our elements have to share these 8 electrons so that everyone ends up with a full valence shell. Well, like we just saw, the single electrons tend to pair up. So these 2 electrons between carbon and hydrogen will become shared, and that will hold true all the way around. So now carbon has 8 total electrons. It has 4 bonds, 2 that it's sharing in each for a total of 8 electrons. Hydrogen only needs 2 electrons to be stable because only 2 electrons are required to fill its valence energy level, and it has those 2 electrons then that it is sharing with hydrogen. Everyone's stable. We only used our total 8 valence electrons. We're good to go. If we take a look at our carbon dioxide, we can follow that same basic process. Our least electronegative, which is carbon, goes in the center. We're going to stick our oxygens around it. Well, I know carbon has 4 valence electrons. Oxygen has 6. So then oxygen likes to form 2 bonds. Carbon likes to form 4. So taking a look at this, for carbon to form 4 bonds, it's going to need a double bond on both sides, which also gives oxygen the 2 that it likes. Well, carbon then has its 8 valence electrons that it needs to be stable, but oxygen right now only has 4, so we can draw in 4 more for it in sets of lone pairs there, and now our oxygen has 8. So oxygen has 4 to itself, 4 that it's sharing with carbon, and then each carbon has 8 as well. It just has to share all of them, but they each get that full valence shell of 8. If we check the total number of electrons in our drawing, we have 16 valence electrons, which is perfect because carbon had 4, each oxygen had 6, and that adds up to our 16 valence electrons in total that we should have. So then, taking a look at this next one, CH2, again, we're picking out that central element, and in this case, it is carbon. Everything else is going to go around it. So I'm going to put my oxygen and the 2 hydrogens around it. Well, I know hydrogen has to be connected with a single bond to my carbon. That makes hydrogen stable. Carbon likes 4 bonds, so it's going to need 2 more. Those other 2 bonds are going to go to oxygen. Oxygen likes 2 bonds, so it's good. But it still needs some more electrons because it needs a total of 8 as well. So it gets 2 lone pairs. So our oxygen has 4 to itself, 4 that is sharing. Carbon has 4 bonds to give it 8 electrons. So we should be good to go. We can check our total number of valence electrons. And we have 12 valence electrons, so let's see if that matches up. Carbon had 4, each hydrogen had 1 for 2, oxygen has 6. So, yep, that adds up to 12. We have the correct number of valence electrons. All of our atoms are stable with that full valence shell. We're good to go. We're going to look at just a couple more examples here real quick with our polyatomic ions. So remember, we have to add or remove electrons whenever we have those charges. A negative charge means that our polyatomic ion here has gained an electron. We're going to add that electron to our central atom, which is nitrogen. Nitrogen then, instead of having 5 valence electrons, is going to have 6 valence electrons. That leaves 2 single electrons, which is where our hydrogen is going to attach to. Here we have a total of 8 valence electrons, which is perfect because we have 5 from nitrogen, 2 from hydrogen, plus 1 because of that charge. So we get a total of 8 valence electrons in our structure. For plain old NH3, nitrogen has 5 valence electrons. 3 of them are single. So those where our hydrogens are going to attach. Again, we have 8 total electrons. 5 plus 1 from each hydrogen is 8, so our total number of valence electrons matches up. Lastly, that positive charge means we've lost electrons, so now we're going to take one away from nitrogen. Nitrogen gets 4 valence electrons. Each of those is going to get shared with our hydrogen. Everyone ends up stable, and we use just our 8 valence electrons that we have. We have 5 plus 4 from our hydrogens, but we got to take one away because of that charge. We did forget one thing on these polyatomic ion Lewis structures, and those are our brackets. Polyatomic ion Lewis structures get brackets and the charge on the outside. So brackets and charge on those 2 polyatomic ions that we just drew. Well, we do have some exceptions to the octet rule. So the octet rule is the fact that these guys want 8 valence electrons to be stable. We've seen one of the exceptions, and that is hydrogen. Hydrogen will have less than 8 valence electrons. It only gets 1 bond or 2 electrons because that's all it needs to fill up the first energy level and to be stable. Beryllium and boron are weird in the sense that they're stable with less than 8. So beryllium's stable with just 4 electrons, which is 2 bonds, as we see in this structure here. Beryllium itself has 2 valence electrons, so it likes to form 2 bonds. In order for it to gain 4 more electrons from somewhere, to get to 8, that takes way too much energy. It'd rather just chill with the 4 electrons and be good to go. Similarly, boron has 3 valence electrons, so it's just going to form 3 bonds. It is perfectly stable with 6. The energy that it would take to gain 2 more to get to 8 is just not worth it. So it's just going to be stable and happy with those 6 electrons. So boron will always have 3 bonds, and beryllium will always have 2 bonds. Our other big exception to the octet rule is those elements that can have more than 8 valence electrons. Anything in period 3 through 7 can expand their octet to have more than 4 bonds, more than 8 electrons, and will typically have anywhere from 10 to 12 electrons in it. We can only do this in periods 3 through 7 because they hold those extra electrons in those empty d orbitals. Once we get to period 3, our valence electrons are in the 3rd energy level, and the 3rd energy level has sp and d orbitals. However, those 3d orbitals aren't filled yet whenever we're at like phosphorus or something that's in the 3rd energy level. All those 3ds are there, but they're all empty because we haven't made it to the point where we need to put electrons in it. If you have extra electrons that you need to put in your structure, they're going to go on the central atom. You just need to double check and make sure that your central atom is something that can have an expanded octet. So looking at these couple examples here, arsenic has 10 electrons. Well, that's okay. Arsenic is in the 4th period. It's in the 4p3 spot. It still has all those empty 4ds that it can use to bond with. Sulfur here has 12 valence electrons, which is also okay. Sulfur sits in that 3p4 spot, but all of its 3ds are still there and empty, so that's where these extra electrons are going to go for bonding. Let's look at drawing a couple of these exception ones. On this first one, we have radon dichloride. Radon's a noble gas. Noble gases don't typically bond because they already have a full shell, they're already stable, but they certainly can bond and do sometimes in a compound like this. So we know all the valence electrons we start with, we have to have in our structure. So radon has 8 valence electrons. We have 2 chlorines. Each of them has 7 valence electrons. So that gives us a total of 22 electrons that we need in our structure. Radon's the least electronegative, so it'll be in the center. We'll put our chlorines on the outside. And chlorine has 7 valence electrons, so it just likes to form that one bond to the radon. So at this point, both of our chlorines are stable. They have their full valence shell of 8, but we still have more electrons that we have to use. Right now, we've only used 16 electrons, so we're going to need 6 more. Those other 6 electrons that we need are going to go on radon as lone pairs. Well, now radon has 10 valence electrons, but again, that's okay. Radon is in the 6p6 spot. It has all the empty 6d orbitals still that it can use for bonding. Quick look at beryllium dihydride here. Beryllium has 2 valence electrons. It likes 2 bonds and is going to bond to hydrogen. Our structure has a total of 4 valence electrons, which is perfect. Our 2 from beryllium and 1 from each hydrogen. So we're good to go there, and beryllium is perfectly stable with just those 4 electrons. So there is some more practice on page 17 and 15 on drawing those Lewis structures for you to try out and get in the swing of this on your own.